and she's going to tell us about not statistic, not reduction for a lattice polygon model. Well, that's what it says here.
Just a quick, it's kind of fuzzy, but just to show you where Saskatchewan is, following Lynn's lead, we're sort of the Texas of the North. So here's Texas, we're almost due north. We get all their birds in the summer. They fly, we're in the flyway between Texas and the Northwest Territories. So that was just a quick. Okay, thank you. I can't read it on here. It's too small. Okay. All right. So thank you very much to the organizers and also to the Newton Institute for being such kind hosts and inviting me to participate in this wonderful conference. Now it's my turn to be nervous after following such beautiful talks about beautiful experiments. I'm going to be talking about a simplified model. So I'm actually going to reverse the order. I'm going to talk about the implications to knot reduction first, and then I'll talk about knot statistics. And the simplified model that I'm going to talk about is a strand passage model that I developed in collaboration with my former graduate student, Michael Safran, and we continue to work on it together. And for those of you who know him, he recently got a tenure track position in the School of Public Health at the University of Saskatchewan, so it's quite good news. Then when I do talk about the knot statistics, that's work done in collaboration with some students, particular summer students, Marla Cheston and Kevin McGregor. And I won't talk about Matthew Schmerler's work, but I may mention it in terms of our future work. And I will talk briefly about some unknotting and chirality-based theory that was done in collaboration with Marielle Vasquez and Koya Shimakawa and Kai Ishihara, who are all here in the audience. And I'd like to also acknowledge funding from NSERC, Natural Sciences and Engineering Research Council of Canada, and also we used quite a bit of the computing facilities of Compute Canada's WestGrid. Okay, so our simplified model is aimed at trying to understand type 2 topolymerases, as Tony Maxwell introduced in his talk. And as he told you, they perform strand passages and they break double-stranded DNA and pass one strand through another. And our involvement or our interest in this goes back to when Michael attended a short course, PMMB short course back in '98, and DeWitt Sumners gave a talk there and posed the question, if local strand passage occur at random locations in a polymer, how efficient is this action at changing knot type? And so my involvement in studying polymers has been based on using lattice models. And so when Michael came, I wasn't at the workshop, but when Michael came back all excited about looking at this question, I first thought, okay, let's develop a lattice model to look at this. So from my perspective, so I'm interested in lattice models of polymers in general. And so when we're thinking of DNA, double-stranded DNA, I'm just going to be representing its conformation on a large scale as a single single polygon on the lattice. And so this is a self-avoiding polygon on the lattice. So the advantages of using the lattice are you can include the excluded volume property quite easily, and but yet there's still substantial conformational freedom for these polygons. And you can also do some nice mathematics, so combinatorial and asymptotic analysis is possible. But there are also some critical exponents which are expected to be exactly the same for the lattice models and real polymers. Okay, so what we did was we decided to model the situation where the topoisomerase had already bound to the DNA or the ring polymer, and we assumed that the shape at the binding site was like this. So we looked at polygons which have this fixed structure in them, and so this was roughly modeled after what the Berger et al. Picture of what DNA looked like at the strand passage site. And so we already have this kind of a bend in there, but we're not saying about how the bend got there, or whether the the topoisomerase created it, or whether that it was binding preferentially at such a place. And then we performed strand passage by just flipping one thing over the other, and basically replacing this structure in our polygon by this structure. Okay, and so essentially what we do is we're interested in what we call knot transition probabilities. So if I start with a polygon with a given knot type and this structure in it, and then I perform strand passage, what's the probability that the knot type gets changed? And so if I start with an unknot, what's the probability that I get a trefoil, or what's the probability that I stay the unknot? So in our model, each polygon with the same number of edges is considered to be equally likely. So this is what's considered to be a good solvent condition. Okay, and I will say later that we can say something theoretically about these knot transition probabilities, but we're quite limited in what we can say theoretically. So instead, we wanted to estimate these numbers using, we used Monte Carlo simulation to estimate these knot transition probabilities. And the way we do that is we generate a set of polygons of varying lengths that, and fixed knot type that contain this structure. And then when we get a sample of these polygons with a given knot type, then we just perform the strand passage on each of them and look at how many give you the same knot type that you start with, how many give a different knot type, and so on. And we can calculate the probability, we can estimate the probabilities based on that. So in order to do that, we need a computer Monte Carlo algorithm that generates polygons with a fixed knot type and with this structure, and generates them so that the equilibrium distribution, or the equilibrium distribution is the one where each polygon of the same length is equally likely. So what works is the BF-ACF moves. So you start out with any polygon and you can perform one of these moves. So if you have a 90-degree angle, you can flip it, or you can go back. Or if you have a single edge, you can bump it out. So you can change the length, bump it out, or if you have one of these, you can go back to that. So these are the BF-ACF moves. And it was proved by Jansen, Rensburg, and Whittington that these moves are essentially equivalent, that you can perform all the Riedemeister moves for the knot theorists on a polygon using sequences of these moves, And so you can sample polygons with fixed knot type using these moves. And so what Michael did in his master's thesis is he proved that you can use the same moves and sample polygons with the same knot type and with this structure fixed. So there's just one slight difference between without the structure situation and with the structure is that we get what's called 2 ergodicity classes instead of 1, where what I mean by that is, so the 2 ergodicity classes end up corresponding to whether you have a plus crossing or a minus crossing at the strand passage site. Or another way of saying it, so we've got this fixed structure, so that if I look at this endpoint here, C, it has to be part of a polygon. So either I can join C to D, as in this picture, or C could be joined directly to H. And so this gives these 2 classes. In this case, when C is joined directly to D, then we have a minus crossing at the strand passage site. And in this case, we have a plus crossing. Fortunately, the 2 classes, one can be obtained from the other by a mirror image. So we can actually just focus on one class and learn everything about both classes. Okay, so, but what it means is we can also look at strand passages which are unidirectional. So we can focus on what happens if we just change a minus to a plus, or if we just change a plus to a minus when we perform the strand passage. Okay, so we use this to try to see if we could add something to an understanding of the topoisomerase topo2 action on DNA. And so the DNA experiments of Rybankov et al., which have been mentioned, showed that, and I think as Andre pointed out, these were on relaxed DNA, that topo2, type 2 topoisomerase reduces knotting from equilibrium as much as 80 times more. So there's 80 times fewer knots when you use, when you have type 2 topoisomerase in your solution than you would expect if you just randomly cyclized DNA and looked at the knot distribution. So in their experiment, they looked at this fraction of knots at equilibrium and compared it to the fraction of knots at the steady state obtained using type 2 topoisomerase. So Lin and co-workers looked at a lattice model first for the this type 2 topoisomerase interaction, and they introduced something called a knot reduction factor, which is the ratio of knots to unknots at equilibrium divided by the ratio of knots to unknots at steady state. And so in particular, if this knot reduction factor is bigger than 1, then the ratio of knots to unknots at steady state is smaller than at equilibrium. So one would say knotting has been reduced. And this RK, this knot reduction factor, can be written like this, where this is the probability of being knotted at equilibrium. This is the probability of being unknotted at equilibrium. And then these are knot transition probabilities. This is the probability of going from a knot to the unknot at steady in the topo2 interaction. And this is the probability of going from an unknot to a knot. So if you know the equilibrium distribution and you know these knot transition probabilities due to your strand passage operation, then you can get this knot reduction factor. And what Lin and coworkers showed is that the knot reduction depended on the local geometry at the strand passage site. It's called the juxtaposition geometry. And they found that knot reduction was greater for hooked juxtapositions as opposed to, say, half-hooked or not hooked at all juxtapositions. All right, so and then I heard about some interesting DNA experiments, single molecule experiments, I believe, with a bead and a braid, similar to what was discussed in our last talk by Newman et al. This was in the NICE Kyoto conference a couple of years ago. And they showed that, or their results indicated that type 2 topoisomerase had different reaction kinetics when it was dealing with positive supercoiling as opposed to negative supercoiling, in the sense that it removed positive supercoiling more likely than negative supercoiling, where the first one was done processively and the last one distributively. And they also found an interaction preference for a crossing angle between the two juxtaposed DNA strands, which is slightly less than 90 degrees. So from this, it seems that the local geometry does play a role in the topo DNA reaction rates, and so topo, and okay, and so geometry, but also whether you have a positive or supercoiling or negative supercoiling. So chirality can play a role. All right, so we wanted to see whether there's any way we could use our model to address this, or to look at knot reduction. So in our model, we already have this fixed structure, whereas Lynn and coworkers, they were varying the juxtaposition. So we aren't changing that structure, but we can look at now the structure around that fixed structure. So we can look at, if we go out an additional edge from each of the endpoints of our structure, and keep track of what that geometry looks like. And we can calculate something called what we call a comparison factor. So it's the ratio of the knot reduction factor for if we only do strand passages at a fixed geometry, which is defined beyond our fixed geometry, compared to if we do strand passages without that further restriction. Okay, and so these are just, as I said, some examples of the different geometries. So the point, so maybe it's clear that this one is different than that one. We call this a Z structure. So the middle thing is part of our fixed structure, and now this one we have one edge coming in that direction and another edge going out. This one we call our straight structure, straight top structure. Our structure is, the fixed structure is here, but now I'm forcing there to be another edge going in here and another edge going out. And the bottom structure is the same for both of these. I call this one S plus because it's occurring in such a way that this C, these arrows are indicating what's joined to what. So C is joined immediately to H here, whereas this has the same geometry at the strand passage site as this one, but now C is joined to D in this one. So I call this one S minus. All right, and we can define an angle associated with one of these juxtapositions by taking a projection down. So this is the projection. And so this is S plus. Remember, C is joined to H in this one. And this is the angle that we define for S plus. For S minus, the angle would be, because in that one C is joined to D, so the geometry is the same, but we would measure a different angle. And we call it an opening angle because, so in the case where C is joined to H, it's a smaller angle because it has less far to go to join up to the other end. whereas when C is joined to D, it has farther to go, so we use the other angle instead. Okay, so we can calculate angles, and we can use the statistics that we get from our computer simulation to calculate this comparison factor, to see how much more knotting is reduced depending on whether we take the local geometry around the strand passage site into account or not. So, but in order to do this, we need to get transition probabilities from a knot to an unknot. And so because the majority, for the lengths of polygons that we're looking at, the majority of knotted polygons are trefoils, we estimate the knotted case by the trefoil case. Okay. Otherwise, we'd have to consider all possible knots as our starting state. And the majority are trefoils, so we don't think we're making such a huge approximation when we do that. All right, so what do we get? First of all, if we look at the knot comparison factor for the different juxtapositions, we find that it does depend on the not just the geometry, because remember, both of these S's had exactly the same geometry at the strand passage site, but it also depends on the crossing sign. Okay, so S plus is the top one, and this is as a function of length. This is this knot reduction factor. Comparison factor is a function of length. Remember, if it's greater than 1, knotting is reduced more. So here's S plus. S minus isn't all that different, but if you compare Z plus and Z minus, Z plus is above 1 for the most part. Z minus is below 1. Okay, so there, and then you can, if you just care about the geometry, ignore the chirality of the strand passage, then that's Z, that's this middle one. Sorry. Okay, so Z plus was these down triangles, Z minus was the squares, and then Z, where I ignore the chirality, is in between. So the point of this is that the chirality does seem to have an influence on the knot reduction. And then when we looked at it as a function of the angle of the juxtapositions, we did find that more or less if the angle was 90 degrees or less, then knot reduction was favored. If the angle was greater than 90 degrees, then the numbers were less than 1. And so this, they did in the Newman et al. Experiments, they found there was a preference for a slightly acute angle, so an angle less than 90 degrees, and so that is favoring knot reduction from what we see. And then we looked at the length dependence of some of these for different angles of these results, and they do seem to be consistent with length, so that there probably is a limiting value as a function of length. So in summary, for that part for the knot reduction, we found that it does depend on both the local geometry and the crossing sign change. And when only unidirectional crossing sign changes are allowed, then knot reduction depends on the opening angle. And on average, only acute opening angles lead to knot reduction. And one of the things we observed in our experiments is that when we were changing a positive crossing to a negative crossing, starting from the unknot, we only ever observed negatively signed knots. That is, we only ever saw negative trefoils. And similarly, when we changed from minus to plus, we saw positively signed trefoils. And so we published these results in these papers. But this last point where we noticed this chirality dependence on the knots that we got, prompted us to talk to our theoretician, knot theory experts, so Koya and Kai and Marielle, and wondered whether there was any theorems about this. So we explored this Progress in Theoretical Physics supplement paper. And we found there was a result that already obtained by others, that the only twist knot which unknots. So the question is, are there knots which can be changed? Are there, if you can change a knot in one crossing to the unknot, are there any such knots where you can either do it by changing a plus to a minus crossing or by changing a minus to a plus crossing? So are there knots where you can do it either way? And the answer is, for twist knots, the only knot that you can do it is the figure 8 knot, and that's not a chiral knot. And then more generally, if you have a rational knot, then there are some that can be switched by both, but the first one has 8 crossings. They all look like this. They can all be characterized like that. And the first one doesn't happen until 8 crossings, and that's 8, 13. So you can either change it to the unknot by switching this one from crossing or by switching this crossing. And then there's some non-rational knots which have the same property, and the first one of those that comes in is a 9-crossing knot. And then there was some others, 9-crossing knots, where the question was open theoretically, and we used our strand passage model to look at those, and we think that they both only have can be unknotted in one direction. We also used our strand passage model to look at, so remember 813 was this one you could switch by either a plus or a minus crossing. And we said, suppose we only allow one direction strand passage, is one of the, if I look at 813 and its mirror image, is one of them more likely to unknot than the other by that strand passage? And we did find for small lengths that there were some differences in this is the unknotting probability for starting with 813 and its mirror image. Okay, so those are some things that we started to look at, chirality-based things. And that's sort of related to knot statistics. So the second bit of my talk, I want to talk about some new results related to our strand passage model, but now trying to better understand the theory. So for the knot comparison factor, we needed those transition probabilities, probability of going from a knot to another knot. And I wanted to understand better what the, and we saw in the comparison factor that there may be some limiting value as a function of n. So in order to see whether that's true, I wanted to look at the components of that comparison factor and see what the limiting properties with length of those were. And so essentially to get these knot transition probabilities, we're looking at counting polygons on the simple cubic lattice. Just to tell you that the counting problem is hard. There's no formula for these things. On the simple cubic lattice, the largest lengths that people have been able to get to exactly is length 32 for all polygons. And it's been proved that you need 24 edges to create a trefoil. And so if you were trying to get at, and then I think it's 30 edges for a figure 8. So you'll only see trefoils and figure 8s at length 32. So you can't use those exact counts to do very much. Theoretically, some things that people have been able to prove are if I let Pn be the number of up to translation of self-avoiding polygons, Pn of phi be the number of those that are unknotted, and Pnk now be the number of those that have some fixed knot type k, then you can prove that the probability of knotting goes to 1 exponentially fast. So this established the long-time Frisch-Wasserman-Delbruck conjecture, and this is due to DeWitt and Stu-Whittington. If you have the probability of fixed knot type k and the whole set goes to 0, and what's believed is that the number of polygons of length n with a fixed knot type k has this asymptotic form, so some constant that probably depends on k, the length raised to an exponent, where this is the exponent for the unknot, and this fk is the number of prime knots in the knot decomposition of k. And then this exponential part is the same, is believed to be the same regardless of what knot type. Okay, and basically this n to the exponent part, why should it go up by 1 for each prime knot in the knot decomposition? The rough idea behind this is that people think that the knotted part, if you have a fixed knot type, that the knotted part is fairly tight in the, is localized in yes, polygon. And so roughly you have, if you've got an unknotted polygon, you have roughly n place of length n, you have roughly n places to put this tight knot. And so that's the rough argument why. All right, so going back to our strand passage model, we're interested in the number of polygons that give a particular knot type after strand passage. We're interested in the probability of that. So if I start with the unknot, then the transition probability is just the number of unknots that give some knot type k divided by the total number of unknots. If I start with some knot other than the unknot, then I have two possibilities. Either I leave that knot and I change the knot type, but the knot after strand passage still has the original knot in its knot decomposition, or I change the original knot completely so that it's no longer in the knot decomposition. And what we believe is that depending on which of these cases happen, in this case, we believe the transition probabilities go to a constant, strictly greater than 0, whereas these we believe goes to 0, like 1 over n. And the idea is, roughly speaking, in the case where you leave the knot unchanged when you do the strand passage, it's like you have n places to put your strand passage structure and n places to put the knot. And whereas if you if the strand passage structure and the knot are in the same place, you only have n ways for that to happen. And so that's why this 1 over n factor is there. Okay, and I don't have time to go through the rough argument, but we, in the case where the knot is still in the knot decomposition after strand passage, we think that the limiting probability should be the same as if I start with the unknot and go to this knot here. Because essentially, if this is not changed with the strand passage, then it's like I acted on the unknotted part. And so if the whatever happens in the unknot case, I should get the same limiting behavior. All right, and so this is what our statistics, what our numerical simulations confirm. So this is on a log plot. These are these knot transition probabilities as a function of length. And the top one, I'll show you a blow up of that on the next slide. Is 3 different situations. It's starting with the unknot and staying the unknot, starting with the trefoil, staying with the trefoil, starting with 4-1 and staying with 4-1. 4-1 is the figure 8. So we get a limiting probability of this to be roughly the same. The error is in the third digit here, and so they're within each other's error. And then the this line here is there's 3 things there. One is starting with the unknot and going to 3-1. The other is starting with 3-1 and going to 3-1 composed with 3-1. And then the third one is starting with 4-1 and going to 4-1 composed with 3-1. And we do get essentially the same limiting value for those three cases. And then finally, these three are starting with the unknot and going to 4-1, starting with 3-1 and going to 3-1, composed with 4-1, starting with 4-1 and going to 4-1, composed with 4-1. And then the other thing, so this is the blow up of that top line. And then the other thing I said is if we change so if we start with 3-1 and go to the unknot, then we're changing the 3-1 part, and we believe that goes to 0 like 1 over n, and these are fits to this form. So this is the exponent L here. So if it was like 1 over n, L would be 1. And we get, for the case of starting with 3-1 and going to the unknot, we get 0.997, pretty close to 1. And starting with 4-1 and going to the unknot, we get 0.982. Okay, and so then just quickly, we also looked at changing our strand passage structure, and we saw that we get different limiting values, but that it's still consistent the way that we expect them to be consistent. So I'll stop there. Thank you.
On the chiral 8 crossing, not 833, I guess it was, you looked at plus crossings on the +1 and minus crossings on the +1.
No, we did the same crossing change on both. So, and looked to see whether there was any difference. So, I forget what it was. So I think 813 has negative ride. No, so positive ride, and 813S has negative ride. But I forget which crossing change we did on this. It was either plus to minus or...
If you change the plus to minus, you sort of decrease the average ride or something, so it'd make it better.
Yeah, but you know what? It didn't seem to go the way that we would have thought. So, yeah.
Say what? Okay.
Yeah, okay, but...
There's a possibility that your results might be sensitive to the choice of the lattice. So maybe it would be a good idea to test some of it on FCC, say.
Well, but everything we showed is that it is geometry dependent. So yes, it will. So it depends on what you mean. The fact that
No, but you say that something is preferred over the other that may be different on another lattice.
Yeah, I'm not sure. Yeah, we're looking at other structures on the same lattice to see whether or not the trends are the
No,
same.
but I mean that
So-
FCC lattice has different connectivity because each side has 12 neighbors as opposed to 6. And that may change things, for instance. I'm not saying that it's happening,
Right,
but
right.
there's a possibility.
Right. I guess our first step was to look at a different geometry on the same lattice and see whether it still holds there. So we haven't finished that, but that's something we're working on. Yeah.
Okay, let's thank Chris again.